Hello and welcome to another episode of the FDM-printed SLA-Printer. This time we try to explain the nanodlp shield design. Warning, this episode is extremely boring if you are not intent to solder this shield. So let's start with a short walk through the schematics of the nanodlp shield that I have designed to get some understanding on what components are needed and their purpose. Also get a better understanding on why they are located and wired the way they are. But one short disclaimer first. I'm just an hobbyist, self-teach when it comes to electronics and schematics, but it works to a certain degree for me and I'm happy to share it with you. Of course, if you are an electronics engineer with a professional education in electronics, you most likely will approach things differently, more professional. So be merciful, and as always, I appreciate your comments and recommendations for improvement. The purpose of the nanodlp shield is to get all relevant electronic components connected to the Raspberry Pi's GPIO port, which is right here above in the schematic. That enables the nanodlp software that runs on a Raspberry Pi to control those components and also to provide them and the Raspberry Pi itself with power. The main power supply for the printer will be a 12 volts 5 ampere external power supply unit. This will be connected to the nanodlp shield via a 2-pin screw terminal, which is located in the bottom left corner of the schematic, right here. Unfortunately, not all components work on the same voltage level, but on 5 and 12 volts. This requires some kind of voltage regulator to step down the 12 volts to 5 volts. For that purpose, a tiny daughter PCB of the type MP1584 is used. This is located right above the 12 volt input screw terminal. You can find it here in the schematic. The use of the MP1584 voltage regulator is quite easy. On the one end, the input voltage is connected with ground and 12 volt, and on the other side, the secondary voltage will be provided again, ground here and 5 volts. One important note, the MP1584 is a variable voltage regulator, which means it can step down a certain range of input voltage to another range of output voltages and need to be adjusted via a potentiometer to provide the right output level. If this is not done properly and the 5 volt components get provided with a much higher voltage level, those components can become destroyed permanently. So this is how our voltage regulator looks like. On the bottom right is the connector for the 12 volt input line and left to it for the ground. Here's a tiny potentiometer that we need to adjust to get the right output voltage level. And on the top, the right connector is for 5 volt output and left to it for the ground. For easier handling, I put the MP1585 with its connectors on a breadboard, therefore it becomes easier to connect the input voltage and attach probes of a multimeter voltmeter. Those two wires come from a 12 volt power supply. The red one is the 12 volt line, the black one ground. Those get connected to the input side of the voltage regulator. Then we need some multimeter that is capable of measuring DC voltages. If you don't already have one, it's maybe a good opportunity to get one. They are not very expensive. Reasonable entry level devices start around 20 bucks. They are very useful. I use them all the time. So let's first check for proper input voltage level of 12 volts. Okay, 1199 is close enough to continue. Now let's see what output voltage level we get without adjustment. 9.09 volts, much too high. Without adjustment, Raspberry Pi, the stepper driver and our HDMI display controller would have been destroyed. So let's start adjustment by turning slowly the potentiometer while checking the readings of the voltage meter. Take you some time to make this right. However, there is a small tolerance range, so that slightly deviations around 100 microvolts shouldn't harm. Yeah, that's close enough. And that's basically all to do to get the voltage regulator adjusted. Now that we have 12 and 5 volts available, let's have a look which components get powered by them. Let's start with those components that consume 12 volts. The first one is a 12 volt fan of the UV LED's heatsink. The pinhead connector for the fan is directly connected to the screw terminal of the 12 volt input. If we follow the line of this pin, it's the 12 volt line, goes along that trace and is directly connected to the 12 volt pin of the input screw terminal. And here the ground pin of the 12 volts go along that way, down that direction, and is connected to the ground pin of the input screw terminal. Another 12 volt consumer is the NEMA 70 stepper motor, but the motor is not directly connected to the power supply, but via the stepper driver, which is located right here. Therefore the two pins of the stepper driver for the motor power are connected to the 12 volt input screw terminal. If we have a look here, this is the pin for the 12 volt input for the motor. Again, it goes along that trace, down the bottom, and is connected here to the 12 volt input of the input screw terminal. The other connector, the ground connector for powering the motor, goes along that way and also directly connected to the screw terminal of the input. The last consumer of the 12 volts are the UV LEDs. Those are high power LEDs. My printer design uses 4 times 10 watt LEDs on 12 volts, which is round about 3.5 amps. To support sufficient wiring, the connectors for the UV LEDs are also screw terminals and located on the bottom right of the schematics, right here. Of course, we need also take care for sufficient wiring of the high current LEDs on the shield itself. This is valid for the 12 volt line that comes from the 12 volt input screw terminal, right here, goes along that trace and connects directly the 12 volts pin of the screw terminal for the UV LED. And of course it's also valid for the ground line that comes from the screw terminal of the input, goes along that way, all around that way, connects to this MOSFET. MOSFET is a kind of transistor of the type IR-ZF44N and continues by the drain pin of this MOSFET, goes down again and get connected to the ground pin of the screw terminal for the UV LEDs. So what's this MOSFET thing? As already said, it's a kind of transistor. It allows us to control devices of higher voltages or higher currents with a GPIO port. GPIO ports also provide, when they used as an output line, a very tiny current, but this is insufficient to power high current LEDs. The way this can be handled is to use MOSFET, which basically acts like a kind of remote switch. You can compare it with kind of relay, let's say. It works in a way that when the GPIO port, which is right here, and in a particular case it's the GPIO port 26, and this goes on high, it causes that the current can flow between source and drain of the MOSFET, which is basically like a switch. When the GPIO port pin goes on low, the current cannot flow, and this basically stops the UV LED from working. This is important because the software nanodlp that controls the print operation need to have control over the exposure time, how long UV LED light will get exposed to the resin and to the build plate, and therefore that's the setup. Well, now let's have a look on all the 5 volt consumers. First of all, it's the Raspberry Pi itself. And the nice thing is, as we have here a voltage regulator, which is nicely adjusted to 5 volts, it's relatively safe to connect the GPIO ports, which has a 5 volt pin and a ground pin right here of the Raspberry Pi to this 5 volt voltage. So this is the output side of the voltage regulator, and the 5 volt gets along that trace and gets connected to these 5 volt pins of the GPIO port, and the ground pin of the voltage regulator output gets connected to the ground pin of the GPIO port. That's basically what's necessary to get the Raspberry Pi powered by the 5 volts of the voltage regulator. Another consumer for the 5 volts is the connector here that provides power for the HDMI display and the HDMI display controller. It's pretty easy. It's directly connected to the voltage regulator. So if you follow the trace, it goes up here, follows that direction up here, and gets directly connected to the 5 volt output of the voltage regulator. The other pin goes that direction, and along that line goes to the ground pin of the output side of the voltage regulator. What else of 5 volt consumers do we have in our schematic? Yeah, it's here the connector for the 6002 I2C LCD display. It also consumes 5 volt, and in addition to that, it needs 2 I/O lines for the I2C interface. Those are here on the GPIO port right above. It's the GPIO port 2 and GPIO port 3, SDA and SCL. Therefore, this location for the 6002 I2C LCD display connector is pretty good located here. And again, the ground of the voltage regulator goes directly here to this pinhead connector. The 5 volts go up that trace, and very easy, the I/O ports that are necessary right above get also directly connected. So let's see, what else do we have? Normal consumers, I think. No regular, at least. The very next connector that we have here on the shield is this 2 pins connector, which is labeled LED. Yeah, and I think I have to explain something about the LED indicator. This LED indicator shall indicate whether it is safe to power down the printer and the Raspberry Pi. Why is this important? Because you need to know that Raspberry Pi is a kind of computer that runs on an operating system which is a kind of Linux. And Linux, if running, usually have open background processes, and those background processes might have open write handles to the file system. And if an open write operation is not properly committed, but instead the power gets cut off, this can cause the file image of the SD card become corrupted. And this is a very bad thing, because this can cause that very next time the Raspberry Pi or the printer gets powered up, the Linux get hang up during boot up sequence, which basically means that the printer will never become ready again. And the only possible way to fix this might be to set up a new SD card file image. And you're lucky enough if you made a backup of the SD card image. If not, you're faced with the situation that you have to set up each and every piece of software with its configuration again. From the Linux over the nanodlp software, also specific profiles for the printer or the resin. So, to prevent this, the best case is to not power down the Raspberry Pi while the shutdown is not performed and not finalized. So, how can the printer and the Raspberry Pi become shut down? There's an option within the nanodlp user interface. Another way would be to press a hardware key, which will be installed in the front panel of the printer. Both will initiate a shutdown sequence, and the shutdown sequence causes all background processes of Linux to probably become terminated. And by doing so, prevents open file handles to corrupt the system. The difficulty on this is that a shutdown sequence can take a couple of seconds, in worst case even a minute, and you can never be on the safe side that the shutdown sequence is already finished. And this is where this indicator LED comes in. The way it is connected works in a way that as soon as the machine is powered on, the LED will be lighted, and the LED will stay on as long as the shutdown sequence is not finished. So as soon as you initiate a shutdown sequence, either by the user interface of nanodlp or by pressing the hardware switch in the front panel of the printer, the LED remains until the shutdown sequence is finished. And when the LED indicator light goes off, it's safe to power down the printer and the Raspberry Pi. That's the purpose. And the way it is wired is pretty easy. The one pin that you see here is directly connected to the ground, and the other pin goes over a 100 ohm resistor, gets connected to this GPIO port pin, which is, let's see, GPIO port 14. Just as easy like that. Okay. What's else? The next connector here to the right of the LED connector is also a 2-pin pinnet connector, which is labeled stop key. And this is basically the hardware key that I just explained, which resists on the front panel of the printer. When it is pressed, it causes the printer during an ongoing print operation to stop the print operation, and if no print operation is ongoing and the hardware switch is pressed, it causes the nanodlp to initiate a shutdown sequence. So the way this switch is connected is again quite easy. The one pin is directly connected to ground, and the other pin here gets connected on the one side to an available GPIO port. In that particular case, the stop key is, let's see, stop shutdown switch is GPIO port 27. And speciality is if we use a GPIO port for input, we need to also connect it to 5 volts via a so-called pull-up resistor. Those pull-up resistors are 10 kilo ohms resistors, and they go via the resistor to 5 volts, which is here the case. Okay, what's next? Then we need some end-stop switches. They are located here. Of course, not the switches themselves, but the connectors for the switches. They are very similar in terms of wiring like the hardware switch for stop and shutdown, which basically means they are connected to ground. So this middle pin for that connector and that connector, if you follow that blue line here, that goes along that way and finally gets connected here to the ground pin of the voltage regulator. By the way, if you wonder why we have 2 end-stop switches, this is because we support a bottom switch and a top switch. The bottom switch is in the housing of the printer. The top switch is at the end of the Z-axis rail, and therefore both sides of the Z-axis can be detected. Yes, the middle pin I already explained, it's a ground pin. The top pin in both cases are connected again to available GPIO ports. For the Z end stop at the bottom, it's GPIO port 25. That's the trace that goes along that way, here to that pin of the GPIO port. And for the send end stop switch at the top, it goes along that way to that pin, and in that case it's GPIO port 13. And again, as previously, because they are input lines or input ports, they again need to have a pull-up resistor that goes to 5 volts, and this is where these 10K resistors are for. So the signal pin here of the connector for the end-stop switch goes to a 10K resistor, and from the 10K resistor it goes down here along the trace to the 5 volts. The same is valid for the other Z end-stop switch here. Also from the signal pin over 10K to 5 volts down along here. So in theory, the signal pin and the ground pin are sufficient as long as we go for a mechanical switch. But if you intend to replace a mechanical switch with, let's say, an optical switch, you also need 5 volts to drive that. And this is why we have a third pin that is also connected directly to the 5 volts. So third pin along that way, again to the 5 volts of the regulator. If you design the printer like I do and go with mechanical switches, those 2 pins with the 5 volts are not really needed and can remain empty. As I already said, a simple mechanical switch only gets connected to the signal pin and to the ground pin. So much about the set and stop switches. I think the easy stuff has been discussed, and this leaves us with the stepper driver. So how need the stepper driver and the stepper motor get connected? Well, to get a better understanding on the connectivity, let's have a look on a schematic for a similar purpose. If you're familiar with FDM printing and might have already assembled or made up an own design for an FDM printer, you might be aware of the REMS shield that gets connected to the Arduino Mega. And the REMS shield makes also use of the stepper driver, and yeah, let's have a look on the schematics of the REMS shield to understand or see how the stepper driver needs to get connected. So let's have a look on the schematics of the REMS 1.4 shield, which is typically used in conjunction with an Arduino Mega when it comes to build an FDM printer. There are a lot of details explained that we can ignore, that are not relevant for us. We are only interested in the middle area that describes the connectivity of the stepper drivers. So let's have a closer look on that. And as you can easily recognize, those schematics are much more professional designed than mine, so they are not from me, of course. They are from much more clever people, and yeah, we can make use of it. Well, in the center we have the A4988, but it's just one example for different types of stepper drivers. Most stepper drivers are pin compatible, which basically means they can be replaced as they have all the same type of wiring. Let's start with the right side of pins, and on that one let's have a look on the top side. There are 2 pins labeled VMod and ground. We already had a brief look on them previously. They are to power the motors. So VMod basically means voltage for motor, and the ground pin for that. And when we have a look on this addition to the schematic, this basically says that the 12-volt pin and the ground pin shall be interconnected with an 100 microfarad capacitor. So this capacitor just gets soldered in between those 2 pins, and its purpose is to compensate fluctuations in the provided voltage. If this is not the case, there's a slight risk that fluctuations in voltage can cause the skipping of steps, which would become a quality issue when it comes to positioning of the axis. So it's a relatively easy measure to compensate that and prevent that risk, and by doing so enhance the quality of the positioning. When we have a look at the 2 bottom pins of the right side, they are labeled VDD and ground. They are also purpose is for getting power supply. But in that case, the provided power is only on 5 volts, and its purpose is to power the circuit of the stepper driver itself. So that's the voltage for the motor, that's the voltage for the circuit. The VDD gets connected to the 5 volts, and the ground gets connected to ground, of course. That leaves us with another 4 pins in the middle. They are labeled 2B, 2A, 1A, 1B. And as you can easily see, they get directly wired to a 4-pins pinhead connector. And that's the pinhead connector that the NEMA 70 stepper motor gets connected to. Just as easy like that. That completes the right side of the stepper driver. Let's have a look on the left side here. Let's start with the more easy pins. the one in the middle here, the one is labeled reset and the other is labeled sleep. They are just connected to each other, just that easy like that. The two next pins labeled step and direction, they are just get connected to one available GPIO port. The one is the step pin. That basically means every time when the GPIO port gets on high, it causes the driver to move the motor exactly one step. So basically what the software and the GPIO port does, it pulls the steps, and for each pulsed step the motor goes makes a certain motion, a controlled motion, very precise. The other pin labeled direction or dir also gets connected to an available GPIO port, and this allows the software and the Raspberry Pi to control, as the name says, direction, how the motor turns, clockwise or counterclockwise. So those two pins basically are the most important pins when it comes to control of the motion of the motor. So what else do we have? Let's have a look on the topmost pin called or labeled enable. That's this one here. Pretty much the same like the one beneath. It also needs to get connected to an available port of the GPIO port. And the use or purpose of this pin is basically to switch or enable the motor, set it on and off. If you already have experience with NEMA 70 stepper motors, when they are enabled, they have a high holding torque which prevents you from moving the motor or the axis manually by hand. When you switch it off, this causes the motor coils to power down, and when this is the case, the motors can turn manually, which allows you to manually turn the axis. Different to the other pins, it's not only sufficient to connect this pin to an available GPIO port of the Raspberry Pi. In addition, it needs to get connected via a 10K ohm resistor to 5 volts. Just that easy like that. Also not very difficult. Okay, that leaves us with the last three pins that are labeled MS1, 2 and 3, where MS stands for microstepping. So what is this for? As you might know, the way stepper motors work is that they move in very tiny steps around the axis. Typically a NEMA 70 motor has 200 full steps to make one complete revolution of the motor shaft. And this basically defines the precision and granularity of the motion of the motor. And if we are in need of much more precision for positioning, then we need to break down those full steps into so-called microsteps. And this is the concept behind microstepping. And the A498 stepper driver, for example, supports this kind of microstepping. And this can be configured by connecting these MS1, 2 and 3 to 5 volts or not. As you can see in the schematic, this describes an open connection of MS1 2 voltage and an open connection to 2 voltage and so on. So to get this connected, this is typically done with either some tiny micro switches or so-called jumpers, small tiny connectors that get on top of male pinhead connectors to get the connection closed. And by having 3 of them, this allows for numerous variations for setting up these microsteppings, and depending how they are connected and configured, it goes from full step, this is for example now the case when all connections are open, up to 1/32th of a step for the case that all 3 are connected. So now that we understand what the purpose of those pins are and how they need to become used, let's have a look on how they are wired. Well, most important of this is that all 3 pins go to either a tiny tip switch, which is a bank of 3 switches that can be switched on and off, which we intend to do, or Alternatively, we use some pinhead connectors that we can bridge by putting a jumper on top of it. Both will work. And on the other side, each pin or connection will go to ground, 5-volt ground, of course. But it's not all that is sufficient. In addition to that, we also need to connect the MS1 pin over a 100K resistor to ground. So, also not very difficult, we just need to keep this in mind. Okay, this is the general setup, how it is described in this case of the schematic for the RAMS 1.4. And let's see how we can make use of that in our own schematic for the nanodlp shield. Okay, now let's see how the RAMS design for the stepper driver connectivity fits into our nanodlp shield schematics. And as you can see, the stepper driver is already located almost in the middle of the schematics right here. Just for some reason it's skipped by 90 degrees, so instead of having a right side of pins and a left side of pins, we have a bottom side and a top side of pins. But of course the pins are the same, they have the same purpose, and they have the same connectivity like before explained. So let's start in the same order like before. Let's start with the V-mod, which is the voltage for the motor, the power supply for the motor, and that line is directly connected here to the 12 volts of the 12-volt input screw terminal, and the ground line goes along that trace here up along and gets also connected to the screw terminal for the power supply, of course this time with the ground pin. And as explained previously, the ground and the 12 volts for the motor power supply shall be interconnected via an 100 microfarad capacitor to compensate fluctuations in voltage to prevent quality issues. And this type of capacitor has a polarity you must be aware of. The capacitor has indicators to tell you which pin of the capacitor is plus and which is minus. Make sure that you connect them in the right way to the tooth pins of the stepper driver. On the other side, we have also power supply to the stepper driver, and this time it's about 5 volts that are necessary to power the stepper driver circuit. And this is the VDD pin, which is connected along that trace to the 5 volts of the voltage regulator, and we have here the ground pin that goes along that trace up that way to the ground pin of the voltage regulator. And by doing so, we have the stepper driver circuit powered by 5 volts. That leaves us with another 4 pins right here in the middle. Those 4 pins are labeled 2A, 2B, 1A, 1A, 1B, and are the lines that get connected directly to the NEMA 70 motor, and for that purpose they are wired here to a pinhead connector, 4-pin pinhead connector. By the way, there's an important note, please be aware, we have here on the schematic lines that are crossing. This does not mean that those lines get electronically connected. And the opposite is valid. Make sure that they cannot get electronically connected. We might cross them when we wire the circuit, but if we need to cross those lines, make sure that the one or the other line is isolated to prevent the connection. Otherwise we get short circuits and nothing will work. This is valid for a couple of other crossings, like here where the 5 volts crosses the ground line. Keep them separated as already explained, the same as here. And also here, this almost looks like the same, but it is not. This is the 5 volts and the other line is the 12 volts. Again, keep them separated by using isolated wires. Do we have some other crossings? Yes, we have. We have also here crossings, same is valid for here. Do not get them electronically connected. Use isolated wires to prevent them from connecting to each other. If we intentionally want to have electronic connections, this is the case here, then we have this kind of knot or circle here, which shall indicate that those blue lines are interconnected or those red lines are interconnected. In other cases of crossings, keep them separately. Okay, So that completes us with the bottom side of pins of the stepper driver. Now let's have a look on the top side of pins of the stepper driver right here. Let's start with the more easier one. Those are the two here in the middle. Those are the sleep and the reset pin. As already explained previously, they just get interconnected to each other. Just a short trace here. Again, we have here the direction and the pin. The direction and the step pins here. They need to get connected to an available GPIO port. As indicated here, they go along that trace, up that way, and get connected to the GPIO port here, and that goes almost the same way, up that way, and get connected to another available GPIO port. And let's have a look. The direction pin shall get connected to GPIO port 22, and the step pin need to get connected to GPIO port 23. As already explained, be aware of that crossing. Prevent connectivity of those lines by using isolation. So then we have here the enable line. Again, this goes up to an available GPIO port of the Raspberry Pi. The enable pin shall be connected to GPIO port 24. And as explained previously, in addition to that, we need to have this connected over a 10K resistor to the 5 volts that are here. Well, that leaves us with the microstepping pins, which are the 3 pins here. I intend to use a dip switch, which is basically a tiny component which consists of 3 switches that can be closed or opened and are directly placed beneath the pins for the microstepping of the stepper driver. So in a way that we can connect MS1 to one of those pins here, and MS2 also, MS3, each of them separately. The other side of the tip switch can all be interconnected and go to 5 volts, as easy like that. And there's one more thing to go. The MS1 line needs to go over a 100K resistor to ground. So this is ground line, and go again that trace to the ground line of the voltage regulator here. And again, as we still have some space available beneath the stepper driver, I decided to place the 100K resistor right here beneath the stepper driver. So, and this completes the nanodlp shield schematics. I think we have completed all components, explained the purpose and how they need to get wired.